Fury of Hurricane Noelani stunned weather experts yesterday.
Devastating hurricanes in Hawaii. Giant hailstorms in Tokyo. Tornadoes in Los Angeles. Tidal waves swallowing New York. The world is ripped apart by a climate change cataclysm.
I think we've hit a critical desalinization point.
An unprecedented situation that unleashes unforeseen consequences as ice sheets suddenly shroud the entire Northern Hemisphere.
If we don't act now, it's going to be too late.
Widespread flooding has slowed.
This disaster scenario is depicted in The Day After Tomorrow, a Hollywood blockbuster that grossed $552 million worldwide.
The film was actually quite a big hit. The movie made the AMOC extremely famous.
In the film, the AMOC, the Atlantic current that regulates part of the world's climate, is on the verge of collapse. When the movie came out in 2004, scientists scoffed at the idea. But today, it doesn't seem so preposterous.
We may expect a significant weakening of the AMOC during the 21st century.
The collapse could happen in only 30 years.
What made some scientists reconsider? And what are they learning about the ocean current's role in regulating the global climate?
It's a kind of physical pump that drives the whole dynamics of the oceans.
Could the weakening or even collapse of the AMOC trigger the extreme climate phenomena depicted in the film? Is the timescale realistic? Could we survive it?
The potential impacts are huge.
The Southern Hemisphere would suffocate, while the North would have really extreme winters.
It would inevitably lead to migration.
Science fiction or looming disaster? It seems counterintuitive in the context of global warming, but is the Earth on the brink of a new ice age that can't be stopped?
And we really need to understand sort of a worst-case scenario.
Has the countdown already begun? In 2004 saw the release of a disaster movie about climate change called The Day After Tomorrow, directed by Roland Emmerich, the world-famous science fiction filmmaker and master of ultra-realistic special effects.
Emmerich is a German director known for films that are visually very relevant and powerful.
After Stargate in 1992, Roland Emmerich achieved international acclaim in 1996 with Independence Day. It was a triumph he repeated in 1998 when he pitted the city of New York against a giant lizard in Godzilla.
A feature of Emmerich's movies is that he was the king of what's known in Hollywood as the money shot. That's to say, an original visually arresting image, the kind you put at the end of the trailer that makes people go, wow, I've never seen that before. So they dash out and buy their ticket.
A money shot like this one of the Statue of Liberty trapped in ice. In The Day After Tomorrow, the director tells the story of paleoclimatologist Jack Hall, played by Dennis Quaid, and his battle to save his son Sam trapped in the icy hellscape of New York City, devastated by the effects of climate change.
The Day After Tomorrow is a disaster movie that tries to say something about the current situation for humanity, at least in terms of environmental awareness.
While the film tackles the issue of climate emergency head-on, it takes the opposite approach to the effects of global warming. Rather than heat waves, humanity is threatened by temperatures suddenly plummeting to -100 degrees Celsius, leading to the formation of ice sheets right across the Northern Hemisphere.
The film is based on a book called The Coming Global Superstorm, which describes a global catastrophe triggered by climate change and impacting much of the world. As America turns into a desert, Bangladesh is beset by massive floods, and parts of Europe become blanketed in a Siberian chill.
Behind these cataclysmic events is the sudden collapse of the planet's main ocean current, known as AMOC, or Atlantic Meridional Overturning Circulation. This system of ocean currents, which includes the Gulf Stream, carries warm water from the equator to Europe, along the eastern seaboard of the United States. warming up the passing cool air of the North Atlantic, it acts like a central heating installation, keeping this part of the globe temperate. When it reaches Greenland, the AMOC plunges into the ocean abysses, reaching depths of up to 4,000 meters, before continuing its journey south towards the Indian Ocean, then cooling the Pacific, where it begins its cycle again at a colossal rate.
To simplify things, we tend to say it's like a giant conveyor belt that constantly redistributes excess energy from the equator to the poles. In other words, imagine 20 million cubic meters of water per second being transported from the equator to the poles over the course of a year.
To give an idea of the scale, it's like more than 100 Amazon rivers flowing through the depths of the North Atlantic. These are enormous quantities of water, much greater than all the rivers and all the water flowing into the sea each year.
It is in part due to the circulation of this ocean current that temperatures are milder in Europe than in, say, Canada, even though both are located at the same latitude. It also ensures the tropics do not suffocate in the heat.
The circulation helps restore a balance between the temperatures in the tropics and those at higher latitudes.
It's a kind of physical pump that drives the whole dynamics of the oceans.
The AMOC, then, plays a central role in regulating the climate. It is difficult to imagine that such a powerful phenomenon, active for millions of years, could suddenly come to a halt. It's even more difficult to gauge the consequences. However, this hypothesis is also explored in a confidential Pentagon report leaked by the press in the year of the movie's release, despite attempts by the Bush administration to bury its conclusions.
In 2003, a couple of consultants for the CIA published a report about the risk of an AMOC breakdown with a kind of heading, Thinking the Unthinkable. It was an exploration of what could happen in the worst case.
What would happen? Well, climate change has consequences for society, which is why the government wanted to prepare for food shortages, famine, lack of access to water, and large population migrations. In short, a huge impact on agriculture, society, and the lives of Americans.
While the report aims to prepare the U.S. government for the worst-case climate scenario, it remains something akin to science fiction, albeit a fiction disturbingly similar to the thesis developed in Roland Emmerich's film.
This is very urgent, sir. Our climate is changing violently, and it's going to happen over the next 6 to 8 weeks.
I thought you said this wouldn't happen for another 100 years.
So what did scientists make of the notion of the AMOC collapsing in the day after tomorrow? Might it conceivably trigger a chain reaction leading to the rapid glaciation of the Northern Hemisphere, as predicted by Professor Jack Hall?
The film's general hypothesis was met with a great deal of skepticism by the scientific community. There was a lot of talk of global warming at the time. Here, we had widespread cooling, so it also created confusion among the general public.
When it came out in 2004, I remember the reaction was that the film was nonsense, that there was no scientific truth to it. The director and writers were decried as charlatans.
Then, 19 years later, came a dramatic turn of events. In July 2023, Peter and Suzanne Ditlevsen, a physicist and a statistician at the Niels Bohr Institute in Denmark, published an astonishing study in the prestigious scientific journal Nature Communications. It revived the previously far-fetched hypothesis that the AMOC is in bad shape and could eventually collapse.
What we've observed in the North Atlantic is a very strange phenomenon that the south of Greenland, we see global warming everywhere except in this area. This area has actually been cooling. And so how can that be when we're warming up the globe that there is an area that's not warming as much?
The temperature anomaly, shown in blue on this map produced by NASA, has been the subject of numerous scientific studies since it began to develop a few years ago. To study the phenomenon, scientists at the Niels Bohr Institute analyzed variations in ocean temperature at this latitude, as well as data collected since 2004 from some 30 sensors located between the Canary Islands and the Bahamas. Their conclusion was that the anomaly may be a sign of a weakening in the AMOC.
We're worried that the AMOC might be unstable in a changing climate. If we're warming up, we get more fresh water running off the ice sheets, and fresh water into the ocean makes the top water lighter, and that could potentially shut down the AMOC.
How could fresh water compromise the correct functioning of the world's most powerful ocean current? In the tropics, some of the water evaporates under the heat of the sun, causing a sharp increase in salinity. The current flows up to Florida and then on towards Greenland, where the surface of the water cools. It becomes so heavy under the weight of the salt that it eventually falls to the bottom of the ocean, much like a waterfall. The force of this undersea waterfall creates a current comparable to that of a river, propelling the salt-laden water toward the Southern Hemisphere, where it is once again diluted before beginning the journey anew. But when large quantities of fresh water are created at the ice cap by the effects of global warming, the salt content is diluted and the water is no longer heavy enough to sink. The process thus grinds to a halt. It is a phenomenon that the Danish scientists fear will intensify if humanity maintains its emissions of greenhouse gases into the atmosphere. The study even goes so far as to provide a rather alarming prediction.
So the conclusion is that the collapse of the AMOC could happen in only 30 years.
In other words, tomorrow. If this prediction proves accurate, the impact on Europe's climate could be severe.
If the AMOC gets weaker and weaker and even shuts down, then this cold blob that we now see in the ocean and above the ocean will get larger and larger until it reaches land areas and covers Great Britain, Scandinavia, Iceland, and leads to some cooling there.
The recent model from University of Utrecht would tell that winter temperatures would be 10 degrees lower and summer temperatures maybe 5 degrees lower in Northern Europe.
Does this cooling mean that the premise of the film, predicting a new ice age, is about to be confirmed? To answer this question, we need to find out whether or not there is a precedent for this phenomenon. And for that, we need to ask a paleoclimatologist.
Paleoclimatologists are researchers who study the climate and try to see how it has changed in the past. They try to establish whether there has always been a Sahara and understand the extent of the world's ice. For example, has there always been ice in Greenland? They do this using the information about past climates captured year after year in geological or biological archives.
For these climate archaeologists, plants, corals, sediments, rocks, and ice caps are a goldmine of information. And the deeper the cores, the further back in time they take us, up to nearly 2 billion years.
The amazing thing about ice cores is that they are composed of ice crystals, which allow us to reconstruct temperature variations and air bubbles, from which we can reconstruct paleo-atmospheres.
Analysis of the ice crystals can effectively determine the air temperature at the time of their creation.
That's how we know that the climate alternated between glacial and interglacial periods.
To understand how the climate might change and what lies in store for us if it continues on this trajectory, researchers look to the past for historical examples.
About 500,000 years ago, the Western European climate was so humid that hippos bathed in the waters of the Thames, and African elephants roamed the Champs-Élysées. Then suddenly, there came an ice age, the most severe we have seen in the last million years.
Over the past million years, our climate has been regulated by a cycle of glacial periods lasting 100,000 years, triggering a rebuild of the polar ice caps that have melted over the previous 100,000 years and so forth. The alternation of the glacial and interglacial periods is linked to the position of the Earth relative to the Sun. These orbital mechanisms dictate the amount of energy coming from the Sun. It's all natural and has always existed.
This slow phenomenon, linked to the Earth's orbit and inclination relative to the Sun, is known as the Milankovitch cycle. According to this natural rhythm, planet Earth should emerge from the Holocene, the warm interglacial period in which we live, and enter a new ice age in about 10,000 years' time. But have more rapid glaciations occurred in the past? Should we be concerned that such a phenomenon might occur in our era?
During these glacial and interglacial periods, paleoclimatologists have identified significant cooling anomalies that cannot be explained by orbital parameters, but rather by the internal processes on planet Earth. For example, volcanic eruptions or a slowdown in ocean currents, which would produce significant cooling over several hundred years.
One of these sudden cooling events, known as the Younger Dryas, occurred about 12,000 years ago.
The episode known as the Younger Dryas was a cooling of around 10 degrees Celsius, which set in over a period of a few hundred years. This cooling is not explained by an orbital process, but by the melting of icebergs in the North Atlantic.
This recent Dryas period was the result of the melting of the Fennoscandian ice sheet and the Laurentide ice sheet in North America, flooding the Atlantic Ocean with cold, fresh water and effectively creating an episode that disrupted the AMOC and triggered a cold period that lasted approximately 1,200 years.
Could the current melting of glaciers due to global warming lead to a similar phenomenon? Because at the current rate, 90% of the planet's freshwater reserves might eventually seep into the ocean.
Every year for the past few decades, Greenland has lost around 280 billion tons of ice, which ends up in the ocean. In Antarctica, it's a little less, at 160 billion tons.
The Intergovernmental Panel on Climate Change is well aware of what is happening at the ice caps because they are closely monitored by satellites. We are losing more and more every decade, and it can only accelerate because we are in a world that is warming.
Global warming can therefore cause a slowdown or even a halt in the AMOC, leading to sudden glaciations. One of these abrupt cooling events occurred not so long ago and provides a glimpse of the potentially alarming consequences.
The onset of the Little Ice Age in the 14th century triggered several phenomena, including social destabilization, which led to significant population loss due to famines, epidemics, and wars.
On a global scale, the average cooling was probably only around 0.5 degrees Celsius.
In human history, according to the analysis of prehistorians, glacial periods are more dangerous than warm and humid periods.
How could we adapt if the cooling went beyond that? Would our civilization be able to survive?
Our current society is based on our current climate system. Where agriculture happens, where we live, is very dictated by the climate.
The crops we currently grow are suited to the recent average temperatures experienced in a particular region. If that temperature suddenly dropped, it would be extremely disruptive and we would see a staggering fall in yields.
Would humanity be doomed to starve? How can we prepare for such disruption? Widespread greenhouse cultivation would become a necessity. Likewise, the development of innovative agricultural methods, such as vertical farms in urban areas, or the use of genetically modified plants able to withstand extreme climates. Another option would be to move production areas in accordance with the shifting climate zones. And that's not all. Sudden cooling would lead to a considerable increase in the demand for energy.
Much colder temperatures mean a greater need for energy to heat the population. We would clearly need an electricity grid able to withstand an enormous demand for power, given that we would need to supply and distribute electricity for heating and everything else.
In the event of a system collapse, population centers could face massive power cuts, causing prolonged blackouts. In extreme weather conditions, mining fossil fuels such as coal, gas, and oil would become increasingly difficult. And in some cases, the deposits would be completely inaccessible. In this context, the development of sustainable infrastructure would be crucial. Solar, wind, and nuclear energy could represent credible alternatives, provided they can withstand the violence of extreme weather events. Over and above production, the entire global energy chain would potentially be destabilized.
It could be a source of tension extending far beyond the affected region. In the modern era, the dependence on resources is virtually a global phenomenon.
Energy shortages, price increases, geopolitical instability. The potential consequences are myriad. Faced with a hostile climate, substantial investment would be required to redesign cities and create new models of housing capable of withstanding extreme temperatures. Perhaps the cities of the future will be partially underground, beneath domes, or thermoregulated structures able to maintain suitable living conditions for human populations. But are we ready to respond to these challenges? Would we be forced to abandon our home regions, as depicted in this migration scene in The Day After Tomorrow, where North Americans seek refuge in Mexico?
And now, in a dramatic reversal of illegal immigration, thousands of people are crossing the Rio Grande into Mexico. The scene that's unfolding here behind me is one of desperation and frustration. People have abandoned their cars, grabbed their belongings, and they are wading across the river illegally into Mexico.
I don't think I would expect that direction of migration, mostly because I think the climate impacts from the AMOC collapse on the U.S. are less certain than is shown in the movie. The places that I'm more concerned about are Northern Europe due to the temperature effect and equatorial regions due to this shift in the precipitation.
Precipitation, which, according to a recent scientific study, could move 500 to 1,000 kilometers southward in tropical areas in the event of an AMOC slowdown or collapse, disrupting the climate and hydrological balance of these regions.
We would see parts of subtropical Africa completely drying up. Scientists have also shown that a slowdown in the AMOC would impact the monsoon in India and thus the rainfall in that part of the world.
Where these tropical rainfall belts haven't been in the past, they will now lead to unprecedented rainfall extremes and flooding. Where people are used to it, where they've always been, they will be confronted with so far unknown drought conditions.
Historical examples seem to support the Danish theory. But is this study reliable? Are we right to be concerned about a potential shutdown of the AMOC by 2050?
The Niels Bohr Institute uses a statistical approach to detect early warning signs of a collapse in the AMOC. This is a very theoretical study based on an equation rather than on complex digital models.
By comparing paleoclimate data with modern observations, Peter Ditlevsen has formulated a mathematical equation to indicate the stage at which the ocean current becomes unstable and risks reaching a tipping point. It's like a set of weighing scales. As long as the forces are balanced, it oscillates slightly. But if one side becomes too heavy or too light, it suddenly tips over. Peter Ditlevsen has predicted that this tipping point will be reached in about 30 years' time, with dramatic consequences for the climate. It's a novel theory, but one that is at the heart of a heated debate within the scientific community.
Is that how the AMOC system works? Can its behavior be explained in a single equation? There may be doubts.
Aside from the issue of whether or not a single equation can explain such a complex system, current data on ocean temperature and salinity only covers a period of around 20 years.
The problem with those measurements is that they don't go far enough back in time. We typically understand from models that the AMOC has oscillations on decadal or multi-decadal or centennial timescales.
Clearly, the data demonstrates only one thing with certainty, which is that the power of the AMOC has varied constantly since observations began in 2004, making it impossible to identify an overall trend.
And so if we want to detect a long-term trend, we really need to have observations that extend over these longer time periods.
So what should we make of the Danish study? Does it really guarantee a new ice age?
This study has since been refuted. Other researchers examined Peter's data and tried slightly shifting certain factors. Did that change the result? Yes, it did. Significantly. We may envisage a collapse taking place in the year 3000. If we look at the latest IPCC report, this collapse is unlikely to occur during the 21st century. A slowdown, maybe. That is the consensus. But collapse seems unlikely during the 21st century.
Because while surface temperature and salinity of the ocean are determining factors in the movement of the AMOC, so too are wind direction and strength. This is particularly true in the case of the Gulf Stream, the northern part of which lies between Florida and Greenland. One of the forces governing these winds is unchanging, and it is called the Coriolis force.
The Coriolis force essentially describes the phenomenon of winds in the North Atlantic, both easterly and westerly, and these winds govern the degree of surface water movement.
So that's not going to change. We'll always have a Gulf Stream. What can change, however, is the position and intensity of the Gulf Stream, which may shift in latitude.
So while it is unlikely that the Gulf Stream will cease to exist, its overall activity is nevertheless a cause for concern among scientists.
If we assume that the world is warming between 2 and 4 degrees Celsius, the Gulf Stream will indeed diminish, which may cause local cooling on a regional scale.
Not an ice age then, but a degree of cooling, particularly in Scandinavia, Iceland, Great Britain, and France. The Gulf Stream may have already slowed down by as much as 4% over the last 4 decades, according to a 2023 study published in the scientific journal Geophysical Research Letters. But what about the AMOC? While it does not appear to be on the verge of complete collapse, how likely is it to slow down, like the Gulf Stream? And by how much? What are the potential consequences?
All the models used to predict developments in the AMOC consistently tell us the same thing, which is that we should expect a significant slowdown during the 21st century by something like 10 to 30, 40, even 50%. The figure varies depending on the model and how it represents the AMOC today and its response to climate change. So there is a great uncertainty about the rate and intensity of this reduction.
To understand this degree of uncertainty, we need to examine how the models that predict climate change are developed. More importantly, how reliable are they on a scale of 1,000 years, 100 years, or even a few months?
A climate model simulates the reality of what is happening in the atmosphere, the oceans, and on Earth over a period of time. To do that, we first need to build a grid.
A grid where the planet is divided into billions of small cubes, like a giant 3-dimensional puzzle. For each cube, scientists record data and calculate the interactions between air temperature, sea temperature, wind speed, humidity, clouds, and even the gases present in the atmosphere. Based on this invisible grid, acting as a giant weather simulator, climate models predict, step by step, the behavior of our planet and its future climate.
Using those models and calculations allows us to predict the climate in an hour, in 2 hours, the next day, the next month, and so on for several decades. We can then use that to tackle a scientific question. We vary the data in the model, increase the amount of CO2, adjust the sea levels, and remove several kilometers of ice to see what happens.
For example, an increase in sea temperature means more water vapor released into the atmosphere, which intensifies precipitation and fuels storms. Clouds can both cool the planet by reflecting some of the sun's radiation and trap the heat emitted by the surface, thus contributing to the greenhouse gas effect. These complex interactions require the use of supercomputers, able to perform billions of operations per second to simulate climate change.
They're like digital cathedrals, and a huge amount of work is invested in them.
And the tighter the grid, or the longer the period being simulated, the longer the calculation. For example, a 2,000-year simulation using a 100-kilometer grid takes almost a whole year to complete. However, despite all the resources deployed, there remains a large margin of error.
There are a number of processes in the models that are poorly understood, poorly represented, and for which we do not have the basic physics equations.
One is that the current generation of these climate models do not include a melting Greenland ice sheet.
Another uncertainty, depending on the model, is the impact of global warming itself, linked to the amount of CO2 pumped into the atmosphere.
In some models, warming is minimal, and yet the AMOC collapses, while in other models, warming is high, but the AMOC remains relatively stable. Why? We don't really know.
I've actually been working for 24 hours straight.
Despite these obstacles, thanks to a NASA supercomputer, our movie hero needs only 48 hours to predict the climate for the coming months. And the verdict is...
This is 48 hours out. And in 7 to 10 days. When this storm is over, we'll be in a new ice age.
As a result of global warming and an exponential influx of fresh water into the sea, the slowdown of the AMOC suddenly reaches a tipping point, triggering major climate disruption. It is no longer a question of centuries or months before the consequences are felt, but weeks. While the speed at which these events occur in the film is implausible, in reality, given the rate at which humans continue to consume fossil fuels and warm the atmosphere, how might this phenomenon evolve?
Projections have been made, and according to the latest IPCC report, the rise in global temperatures will be somewhere between 1.5 degrees and 5 degrees above pre-industrial levels by the end of the century.
At a local level, this equates to an increase of 5 or 6 degrees in Greenland. The effects on the AMOC circulation could be profound, even triggering a state of what scientists call abrupt instability. Even supposing this instability develops over a period of several decades, to what extent might it reinforce the extreme weather events caused by the rest of the ongoing climate change? Torrential rain, floods, giant hailstones, cyclones, Arctic cold. Could the Northern Hemisphere really suffer the extreme weather events depicted at the beginning of the cooling period in the Hollywood film?
Things that we might be worried about in the future climate is sea level rise.
In a scenario where we're able to limit warming to less than 2 degrees, that's an increase of around 30 centimeters by the end of the 21st century. If the temperature continues to rise by up to 4 or 5 degrees, the seas may potentially rise by more than a meter by the end of the 21st century.
This phenomenon, now occurring across the entire planet, is linked to global warming, which is accelerating under the pressure of human activities. It could, however, be reinforced locally by a slowdown in the AMOC in Northern Europe.
In addition to that global rise, get half a meter up to a meter of additional regional sea level rise in the North Atlantic.
Ultimately, how high could sea levels rise if all the ice in Greenland melted? How much of the globe would be submerged? And how would it affect our coastlines? In the movie, the projected figure is 8 meters above current levels. The estimate by American scientists at NASA is fairly similar, around 7 meters.
That would mean a very significant change to coastal areas. Countries that already have very little topography, such as Bangladesh or the Pacific Islands, could disappear altogether. We might also consider our own coastlines.
In France, a large part of the Mediterranean coastline, from the Atlantic coast to the English Channel, would be submerged. In Europe, London would literally be on the waterfront. The Netherlands, Venice, and most of Denmark would disappear beneath the waves. In the United States, a 7-meter rise in sea levels would submerge a large portion of the East Coast, including Texas, Florida, and even New York City, where only the skyscrapers would still be visible. Meanwhile, on the West Coast, the hills of San Francisco would become islands in a new archipelago. But in Roland Emmerich's vision, the main consequence of climate change on the American West Coast is not rising sea levels. The movie depicts giant tornadoes sweeping away everything in their path and devastating Los Angeles. How much credence should we give to this theory?
The country that has the most tornadoes each year is clearly the United States. It is the most tornado-prone country in the world, with something like 1,200 tornadoes per year.
According to the U.S. National Oceanic and Atmospheric Administration, the southeast of the country and the Great Plains in the center are the most affected. The strip that stretches from South Dakota all the way down to Texas is called Tornado Alley.
The state most affected, far ahead of the others, is Texas, with around 120 tornadoes per year.
In this region, a combination of factors produces an explosive cocktail. In the spring, when air saturated with moisture from the Gulf of Mexico rises into the atmosphere driven by the heat, it encounters a cold, dry current of air from Canada, carried by the wind from the Rocky Mountains. The result is an abrupt thermal shock as the vapor condenses, forming a cumulus cloud. The greater the contrast between the air masses, the larger the cloud becomes, growing to gigantic proportions, up to 15 kilometers high, resulting in a cumulonimbus cloud. But before it can turn into a supercell and form a tornado, there is one more decisive factor: wind shear.
Wind shear is the way the wind varies vertically, either in intensity or direction. The stronger the wind shear, the more it will tend to arrange the rather chaotic vortices into an organized vortex.
As these winds collide with each other, it sets them spinning. This spinning storm cloud may then eventually form a column that spins and gradually descends toward the ground.
When the column touches the ground, the tornado is created, with winds reaching up to 250 kilometers per hour. While this phenomenon is common in Tornado Alley, it is an unusual occurrence in California.
Most of the tornadoes in California are actually waterspouts, which are tornadoes that form over water. These are quite common and often spill over onto the beaches. Real tornadoes that form on land are quite rare in California because you don't have the extreme clashes of air masses that you find in the Central Plains.
However, in March 2023, in a rare occurrence, 3 tornadoes formed in California, one of which caused extensive damage in the suburbs of Los Angeles.
The first 2 were very weak, but then we had a tornado with winds of around 150 kilometers an hour. This time the tornado formed in the city center, damaging around 20 buildings, which is pretty exceptional in the Los Angeles area.
An isolated phenomenon, or one that is likely to increase as a result of climate change?
The phenomenon has been the subject of many studies, but the reality is that we are not seeing an increase in the number of tornadoes, either in the United States or in Europe.
Does that mean climate change has no impact on them? Or could it, on the contrary, increase their power? Before answering this question, we must first understand the classification of monster twisters.
Tornadoes are classified according to the EF scale, the Enhanced Fujita scale. So we have EF0 and EF1, all the way up to EF5. It's important to note that they are classified not only according to wind speed, but also destructiveness.
The more intense a tornado, the greater its destructive power. An EF0 tornado with winds of around 100 kilometers per hour can tear off roof tiles, detach gutters, and hurl around debris that can shatter windows. But moving into the higher categories, much more destructive physical effects occur. When strong winds blow into a house through broken windows, they slow down, causing the pressure inside to rise. As the outside wind accelerates over the roof, an area of low pressure is created. This imbalance causes the roof to be torn off, followed by a gradual collapse of the walls. The tornado then moves into the EF4 category. It only reaches the most extreme EF5 level when winds exceed 300 kilometers per hour. Could these tornadoes one day become powerful enough to sweep away entire buildings, as depicted in The Day After Tomorrow?
The tornadoes seen in the movie The Day After Tomorrow seem highly improbable. It's important to point out that the most powerful tornadoes, when they hit cities with large concrete buildings, as we see in the movie, dissipate very quickly. They don't have the strength to fight against such buildings. A situation like that would require an extremely powerful tornado, the likes of which, to my knowledge, has never been seen.
In the movie, while tornadoes ravage Los Angeles, an enormous cyclone, fueled by the effects of the disrupted AMOC, forms over the European continent, eventually covering its entire surface. Faced with satellite images of the gathering storm, the NASA scientist is perplexed.
This is Scotland at the time the temperature dropped.
All the more so as two other similar cyclones are forming in the Northern Hemisphere over Siberia and Canada. What do scientists think of this theory? Is it supported by the laws of physics? Can cyclones this large form over continents?
The largest cyclone ever recorded was Typhoon Tip in 1979, which covered an area 2,200 kilometers in diameter, or 6 times the size of France. It generated winds of 305 kilometers per hour, and although destructive, caused less damage than might be expected, given the violence of the phenomenon. But one of the most powerful cyclones ever recorded was Typhoon Haiyan in November 2013, which generated winds of 315 kilometers per hour and caused immense damage and at least 10,000 deaths, mainly in Vietnam and China.
Called typhoons in Asia, hurricanes in the Caribbean and the United States, or cyclones in tropical regions in Oceania, these names refer to one and the same phenomenon. Some can release energy equivalent to 10 times the Hiroshima bomb. And that's not their only common feature.
A tropical cyclone can't form on land under any circumstances. It requires a source of moisture linked to ocean evaporation.
What's more, the sea must have a temperature of at least 26 degrees Celsius and a minimum depth of 50 meters. Under the effect of heat, warm air rises, carrying with it the evaporated water. At altitude, as the air cools, the water vapor condenses, forming thick clouds. The condensation then releases heat, generating an area of low pressure on the surface of the sea. This draws in the cooler surrounding air, creating a series of converging winds. This movement of air towards the center strengthens the low-pressure system and intensifies the cyclone. But there's more. Under the influence of the Earth's rotation, the winds swirl around the center of low pressure, the eye of the storm. A hurricane has now formed. It then begins to travel across the ocean, gaining in intensity when the sea temperature rises in its path. This is often what happens in the Gulf of Mexico as it approaches Florida, for example.
A cyclone can persist for some time on land, driven by its own dynamics and its own humidity. But as soon as it reaches land, cut off from its source of moisture and dumping its rain, its intensity diminishes.
As such, it is physically impossible for such monster cyclones to form on the European continent, let alone in Canada or Siberia, where the prevailing conditions are cold and dry. The scenario in the movie, then, is completely fanciful at this point. In New York, one of the 3 fictional cyclones has devastating consequences. As torrential rain falls on the population, a tidal wave as high as a 4-story building submerges the Statue of Liberty and floods the city. But is this spectacular scene, as realistic as it is terrifying, based on any real science? The 2004 tsunami that devastated Southeast Asia and its coastal cities, killing nearly 250,000 people, is fresh in the memory. But could a cyclone really generate waves as powerful as a tsunami, capable of engulfing an entire city?
The term tsunami is only used in the case of events triggered by volcanic phenomena or geophysical fractures in the Earth's crust. What we're talking about here is storm surges.
Unlike a tsunami, caused by a sudden shift in the ocean floor, typically during an underground earthquake, storm surges are linked to atmospheric phenomena. They usually develop during powerful tropical cyclones. The drop in atmospheric pressure at the center of the cyclone, combined with the force of the winds, creates a suction phenomenon that draws in a huge mass of water. While on the high seas, this rise measures only a few centimeters, it extends over a huge area of the ocean's surface. When this mass of water reaches areas where the seabed is elevated, such as the shoreline, the volume of water remains unchanged, but its level increases sharply, causing a sudden rise in sea level accompanied by powerful waves. The phenomenon is known as a storm surge.
Storm surges can reach considerable heights, up to something like 15 meters. If they hit an area where the continental shelf has a particular topography, they can also generate enormous floods.
As was the case with Hurricane Katrina in New Orleans in 2005, as well as Hurricane Sandy in New York in 2012, which triggered a storm surge that flooded much of the city, causing enormous damage. So could a cyclone as powerful as the one imagined in The Day After Tomorrow really generate a wave massive enough to completely submerge New York?
A storm surge that would submerge the city? No, but it would probably flood it. No, fortunately, we don't expect a tidal wave to hit New York when the AMOC collapses. That's not how it works.
In the wake of the Hollywood blockbusters Three Cyclones, another extreme threat looms over the Northern Hemisphere.
Were you able to recreate the thermal cycle?
Yes. The storm's rotation is pulling supercooled air all the way down from the upper troposphere.
As the temperature drops to below -100 degrees Celsius, the thermal shock is so extreme that it shatters the windows of Manhattan skyscrapers and freezes everything in its path. Is this theory of cold air being pulled down from the troposphere by the storm compatible with the mechanics of the Earth's atmosphere?
That has nothing to do with the laws of physics. It's totally against the laws of physics.
Absolutely not. Stratospheric air will not freeze when it reaches the Earth's surface because the descending air will warm up.
The air would become so warm that the Empire State Building would not freeze, as it does in The Day After Tomorrow. In fact, the effect would more likely resemble a scene from another Roland Emmerich film, Independence Day. The skyscraper could actually burn. But these scientific approximations are of little interest to screenwriters. Their focus is on something else entirely.
Screenwriter Jeffrey Nachmanoff once told me they are not in the business of making films for a few million viewers, then they would stick to the laws of physics, but they make films for a few 100 million viewers, and then they stick to the laws of Hollywood.
While it exaggerates the effects of climate change for the sake of entertainment, The Day After Tomorrow was nevertheless a pioneering film.
The interesting thing about The Day After Tomorrow is that it made ecology its central theme at a time when it wasn't really being talked about.
With its ultra-realistic special effects, the movie succeeded in raising public awareness about a fundamental climate issue.
It made the AMOC extremely famous, and I think the media world's awareness of it is all down to the film.
While the disasters so graphically depicted may never strike as suddenly as they do in a Hollywood blockbuster,
It's interesting because it is based on scientific data, and because it shows that the systems governing the Earth can and will change.
And while humanity is not threatened by an imminent ice age,
the superglaciation depicted in the film is, in my opinion, science fiction. That's not what we see in the data. It's not what the models are showing us, so no worries on that front. We're definitely not going to freeze to death in 2 years' time.
extreme weather events are nevertheless becoming more frequent and devastating.
We know about the looming disaster. We're experiencing unprecedented levels of global warming. So we need to be aware of it, roll up our sleeves, and take action.
We urgently need to limit greenhouse gas emissions, especially the use of fossil fuels. At this stage, not only must we not be afraid, we must have the desire to progress and to change, and to seek ways to adapt. This has been the defining characteristic of the human race for the last 4 million years.
Because unlike in the movie, humanity is not a helpless spectator in the face of climate events. 20 years after its release, The Day After Tomorrow continues to fascinate and remind us that the warnings from scientists are well-founded. Will it also encourage us to take the necessary steps to ensure that we will not be forced to exist in a future world of unsustainable temperatures?